All right, so we're going to prove one more theorem to end the chapter, but before that, I want to give you a definition. So suppose that we have a field monomorphism, and let me call it actually iota be a field monomorphism. Then we can define a homomorphism. Well, it's still a monomorphism. It's a ring monomorphism. Just a one-to-one homomorphism. Iota hat from polynomials over K to polynomials over L. And we do this in a very simple way. Iota hat of a polynomial over K what should that be? Well, iota knows what to do with the coefficients, right? Because iota says, hey, I can take K coefficients and I can turn them into L coefficients. So if we know what to do with the coefficients and we just need to take K coefficients and turn them into L coefficients, then what should we do for iota hat? Well, we should just apply iota to the coefficients and leave the t's alone. And this is, of course, where K0, K1, all the way up to Kn are in K. Why is iota a ring homomorphism? Let's just notice some things. Well, it's one-to-one. Let's start there. Why is it injective? Well, it's one-to-one because iota is. So if you have a polynomial that goes to 0, all of the coefficients must go to 0, but iota is one-to-one. So it must be that you had plugged in 0 into iota in each of these spots. That is, all the coefficients were 0 to start with. Right. So again, because iota is not a valid argument on homework, but what I said would be a valid argument on homework. All right. Does it break up under addition? Well, really, all we're doing is we're playing with the coefficients. So it's not too hard to show that it preserves addition. And again, it's not too hard to show it also preserves multiplication, although it is a bit tedious because multiplication of polynomials is tedious. But again, it's not difficult. So let's see an example of this happening. So we saw that there is an isomorphism from Q adjoint alpha to Q adjoint omega alpha, and it's given by alpha, roughly alpha maps to omega alpha. We replace all of the alphas with an omega alpha. And this is a common way once we've gotten past all the make sure we understand what's going on phase. This is a common way of defining functions or expressing what a function is between simple extensions. You really just say where the generator goes. So alpha is like the new element that's being added to Q. We leave Q alone and we send alpha to omega alpha. Okay. Now we could write out exactly what the function is, but we've seen that a bunch of times already. I'm not going to do that. Okay, so if I have, therefore, so this is like iota. So we get an iota hat from polynomials here to polynomials with coefficients in this other field. And what does it do, for example? So suppose I have, I don't know, let's see. Remember, alpha is the cube root of 2. Suppose I have the polynomial, I don't know, alpha plus 1 plus alpha t plus alpha squared minus 3t cubed, something like that. Where is that polynomial sent to under iota hat? Well, iota hat is going to replace all the alphas with omega alphas. So here I have an alpha, that's going to become an omega alpha. Here I have a 1, that's in Q, that's left alone. But I have an alpha then, that's we're going to replace with omega alpha. The t is left alone. The alpha squared becomes omega squared alpha squared. The negative 3 is left alone. And then we get t cubed. So notice how we just changed the coefficients, but we changed the coefficients in a way that preserves structure. We changed it with this iota mapping here. All right, so I really want you to think about this as just changing coefficients, and changing coefficients can be done in a way that preserves addition and multiplication. All right, so theorem This theorem is a bit of a head scratcher at first, so it may take you a couple times to see what's going on here. At least when I learned it, it took a couple times for me. So suppose K and L are subfields of C, and we have one of these change of coefficient functions. Actually, it's an isomorphism. It is an isomorphism. What's an example of such a thing happening? Well, the example that we just did. Q out join alpha, Q join omega alpha are both subfields of C. This iota is an isomorphism between them. So think at that example. Let's let K alpha and K beta be simple algebraic extensions of K. Oh shoot, K alpha and L beta, my bad. K alpha and L beta. And L respectively. Such that alpha has minimal polynomial M alpha and beta has min poly M beta, of course, over K and L respectively. Suppose further that iota of M alpha is M beta. That is to say, when you change the coefficients from K coefficients to L coefficients, one of the minimal polynomials the coefficients of it gets changed to the other minimal polynomial. Okay. Then what? Then there exists an isomorphism J from these new extensions, such that when you restrict it to K, it's not the identity on K because K is not necessarily a subfield of L, but it agrees with iota. And J sends the generator alpha to beta. Right, that's kind of a mouthful. And since it's a mouthful, what we do is we illustrate it with a diagram. So that's the theorem statement. Diagrammatically, we have sort of the natural inclusion of K into K join alpha. And we have this mapping iota, which is an isomorphism, which goes to L. And then we have the natural inclusion here. This is just the setup of the theorem. Okay, so in black, the black text is just the setup. All right. What does the theorem tell us? The theorem tells us we can complete this to a J, so conclusion, provided something is satisfied. Iota of M alpha is M beta. So you can complete this, and this is an isomorphism as well. Sometimes we write our isomorphisms with a squiggle to indicate it's an isomorphism. And we can do this in such a way that the following happens. First of all, if I were to start with a K, let me use green. If I were to start with a K here, and I send it over to K join alpha, well, when I just include it in, it stays as K. And then when I apply J, I go down here. K gets sent over to via iota to L, and then it gets sent naturally with the natural inclusion of L into L beta there. It's saying that, hey, when I do this process, I'm just doing iota. So iota and J agree on K. And the second thing that it's saying is that J of alpha is beta. So you can extend this isomorphism iota to J in a way that sends the root of one of the minimal polynomial before iota to a root of the minimal polynomial after iota. Okay, so this is what we call an extension theorem. So let me just say this is an extension theorem. and says we can extend isomorphisms provided a condition. Algebra, there's all this structure, so you have to have conditions, provided the minimal polynomials align. And what I mean when I say the minimal polynomials align is they agree after changing coefficients appropriately. Okay. All right, the proof of this is not going to be hard, and I think I actually am going to do one more video on the proof, because this one's already kind of long, and then an example of this happening.